So we're going to now talk about the connection between the KdV and Schrodinger's equation. So let's just go back and see what we wrote. What we worked out was that, and what we showed here, what we studied was this equation here. So let's just be explicit here about the function here, u. So that was Schrodinger's equations, and this was a parameter in the equation here. And for every u, we could calculate what we called the scattering data. So we calculated these, and we gave you some examples exactly of calculating this. We calculated omega n, which are these bound states or eigenfunctions, and there's a finite number of those. So as we conceive of it here, these omega n's are going to depend on, they're going to be functions of x and t, because u is a function of x and t. They depend on u, which is a function of x and t. So we're going to write them as omega n x of t. And then we calculated the scattering, the other scattering data we calculated was this thing here, where it was e to the ik minus ikx plus some reflection coefficient, which is also going to depend now on time, okay, not on x, because this is the u goes to 0 as x goes to plus and minus infinity. So this is the asymptotic form of these, right? So that's as x goes to negative infinity, and then it was t of k comma t. Okay, and the time comes about because u depends on time, e to the minus I k x. X goes to infinity. Okay, so, and we normalize these eigenfunctions here, so we had the integral from minus infinity to infinity of omega n squared dx is equal to 1. All right, so all good. We've got all these, we've got the scattering data, and we've really got no idea what this has got to do with the KdV yet. So what happens is that u evolved according to the KdV, then these this scattering data evolves in a very simple way, and that's the key point. And we've got to be careful here. I've forgotten one super important thing. Associated with these bound states is an eigenvalue lambda n. So I'll write that here with eigenvalue lambda n. So remember that if lambda's, for lambda positive we get an infinite number of solutions here. For lambda negative, I've got this around the right way. Yeah, so this is for lambda negative, and these are the solutions for lambda positive. All right. So what happens is we take this expression here for and we substitute. It's far from obvious why you do this, into the KdV. Okay, remember the KdV is d by dt of u plus 6u. There's lots of ways of writing it. Sometimes we wrote it as u squared here with a 3. So if we substitute this expression into here and we do a whole lot of manipulations, what we end up with is d by dt of lambda w squared plus d by dx of w dxq minus dxwq equals 0, where q is this expression here. Doesn't matter too much what's going on here or what q is about, because It's not the Q part we're interested in. You can imagine that this is just a matter of grinding through the, all these expressions here with substituting this expression in here. Okay, so what that tells us though is that this is a conservation law. If we integrate from minus infinity to infinity, this is going to be equal to 0. So this is a conservation law. So we integrate from minus infinity to infinity, how this works. And of course this is equal to 0 because it integrates just to give the value at the endpoints, which is 0, because U has to decay, W has to decay. So this is equal to 0. All right, so that immediately tells us that, the W only decay for the bound states. So that's careful, but it immediately tells us that d by dt of lambda is equal to 0. So that the eigenvalues, even U evolves according to the KdV equation. It changes shape enormously. Like if you look at the simulation, if we start out with that square block, it'll evolve into some kind of oscillating thing and then some solitons of various heights that looks completely different. But if you found the eigenvalues of this system and the eigenvalues of this system, they'll be the same. So the eigenfunctions might change, but the eigenvalues are the same. So if you took this U and you substitute it in here and calculate the eigenvalues, you'll get 27.3. If you take this crazy shape here, substitute it in here, you'll also get 27.3 or whatever the numbers are.